This video is the first part about an open-source interferometer project for accurate distance measurements. It primarily covers the design, optical layout, and a little bit theoretical background, but you will also see some laser interference action of a real prototype at the end of the video. I will start with a short introduction on the subject, which you can skip if you know about interferometers. An interferometer is an instrument that measures the interference of waves, typically light or radio waves. They detect small changes in distance, displacement, or other physical properties. By comparing the phase difference between two or more wavefronts, interferometers can make extremely precise measurements. There are many types of interferometers that, for example, can characterize the entire surface of a lens or mirror. In contrast, we focus on measuring a single distance to a target reflector, so that the device can be used as a precise linear encoder. The basic principle of such interferometers is to split a light wave into two beams. The reference beam travels a fixed distance along the reference arm, while the other beam travels along the measurement arm. The two beams are then recombined, and their interference converts the phase information into an amplitude signal. The variation in brightness can then be measured using a photodiode. Let's take a look at the design goals of the project. Being an open-source project, one of the major aspirations is to make the design accessible and reproducible by using low-cost optical components and light sources. Furthermore, the manufacturing process should be reasonably simple, and machined parts should be of low complexity, as commercial products can cost thousands of dollars. This project aims to be a practical alternative with reasonable performance at a much lower price. Another objective is to reduce the overall size for easy integration into small machines. The minimum requirement for my specific applications are listed at the bottom, but I am confident that they can be surpassed in terms of range and resolution. The light source is a key component in optical interferometers. The light wave acts as the reference for measuring distances, so any change in wavelength will inevitably affect the measured values. Additionally, the source should emit light at a single frequency, ensuring a long coherence length. The coherence length determines the effective measurement range, and therefore should be as large as possible. Ideally, the light source is also compact, cost-effective, and widely available. A common light source used in interferometers are helium neon lasers. They can provide excellent stability and have very large coherence length. However, they tend to be large and rather expensive. A tempting alternative is laser diodes, as they are inexpensive and only a few millimeters in size. However, due to their small resonator dimensions, they typically produce light with an unstable wavelength and a temperature-dependent spectrum. Furthermore, only certain models offer sufficient coherence length, and the drive conditions must be chosen carefully. This project shares similar requirements for the light source as holography, but fortunately, the interferometer requires much less optical output power, which opens up a wider range of options for selecting an appropriate laser diode. Overall, laser diodes were chosen for this project primarily for their significant size and cost advantage. To mitigate the drawbacks of laser diodes, their output frequency must be stabilized. This is accomplished by adding a second measuring arm to the interferometer using a material with low thermal expansion. This arm provides a stable reference length, and any phase shift observed here is a result of a change in the wavelength of the light source. Since the wavelength emitted by a laser diode can be slightly tuned by adjusting the drive current, we can create a feedback loop to actively counteract any wavelength drift measured in the fixed reference arm. The electronics and control loop will be covered in an upcoming video. For now, it is only important to know that the output can be stabilized by adding an additional interferometer arm. The second key property of the light source is coherence length, which can be tricky with laser diodes. Note that not all laser diodes are capable of producing output with large coherence length. Those that can need to be operated under certain conditions. On the right, a plot of the coherence length for a laser diode over a range of temperatures and drive currents is shown. This map can vary significantly between different laser diode models and even among individual diodes of the same type. The goal is, however, to operate the diode within one of the blue regions. Luckily, for certain laser diode models, these regions are quite large and temperature control isn't necessary when choosing the correct drive current. For example, the shown green laser diode has excellent coherence length of more than 4 meters right above its threshold current. This is the diode you see used in this video, but I am testing other diodes in near future and provide a list of the results. Many low-power red laser diodes around the 5 milliwatt mark are also good candidates, but the small drivers within cheap laser pointer modules should be avoided, as they exhibit large current ripple and reduce coherence length drastically. I know this has been a lot of theory, but bear with me. It gets more practical soon. The next section explores different interferometer designs from which the optical layout used in this project is derived. A well-known topology is the Michelson Interferometer. It features a simple layout and a low number of optical components. One significant issue is that some light is reflected back into the laser source, leading to unstable operation and a very short coherence length. An optical isolator can help prevent this problem, but it adds cost and complexity. Alternatively, an angled beam path could reduce back reflection, though it is incompatible with a mirror moving over long distances. The layout is also very sensitive to mirror alignment. Mach-Zehnder interferometers do not suffer from back reflections, but require more optical components. Also, the beams are incident on the mirrors at an angle, which limits the ability to make large linear motions of the measurement mirror. A variation of the Michelson interferometer also avoids back reflection by using offset beam paths. This is achieved by replacing the plane mirrors by corner cube reflectors. Due to the offset, the reflected beam misses the laser source and can be absorbed nearby. This design has many advantages enabled by the corner cube reflectors. So let's take a closer look at these great components in a practical demonstration. Corner cube reflectors are optical components that reflect light back in the same direction from which it came. They are commercially available, typically costing between $12 and $15, and are most commonly found in diameters of 1 inch or half an inch. There are 3 types of corner cube reflectors, each differing in their mirror coatings. First, copper-coated reflectors, which have an orange tint, are most suitable for red laser wavelengths. Second, silver-coated reflectors, which are colorless, can be used for any visible wavelengths. Third, uncoated reflectors, which rely on total internal reflection. However, the latter are not suitable for this project, because they can rotate the plane of polarization, which hinders both interference and proper reflection at the beam splitter. For comparison, this clip shows a normal mirror. The direction of the reflected beam changes when the mirror is rotated. However, moving the mirror within its plane does not alter the beam path. The corner cube reflector shows the opposite behavior. Changing the angle of the reflector does not alter the direction of the return beam. Moving the reflector along its front face plane creates a beam offset. So we have seen how corner cube reflectors create a beam offset and require less stringent alignment, enabling the design shown here. However, for the stabilization of the laser diode, we require an additional measurement arm that needs to be incorporated into the design. This is achieved by replacing the beam splitter cube with an ordinary glass plate. Plate beam splitters are usually inferior, since they suffer from double reflection from the front and back face, which is often undesirable. However, this design utilizes this drawback as an advantage to create another beam path for our laser diode stabilization arm. This not only replaces the expensive beam splitter cube, but also allows for tightly packed beam paths with minimal optical components. Coming up with this optical design can be considered one of the key challenges for this project. So far, I am quite happy with it, as it meets several of the previously mentioned design goals. The beam paths can look a bit complicated though, so let's take a closer look. The beam emitted from the laser hits the first surface of the splitter plate. It is divided at point 1 into 2 beams. One is continuing within the glass plate and the other traveling to the upper corner cube reflector, where it is returned back to the detector D2. At point 2, the other beam is split at the exit surface of the plate, reaching the detector D1, as well as the right corner cube reflector. The reflector returns the beam back to the splitter plate, and the beam is divided once more at point 3. One part continues straight, and the other part travels down to the third corner cube reflector, from which it is returned back upwards to detector 1. At point 2, we see the first recombination creating an interference signal at detector D1. At point 4, another split occurs at the exit surface of the beam splitter. Here it recombines with the light from the upper corner cube reflector, creating an interference signal at detector D2. So far, we have one detector for each measurement arm, receiving a sinusoidal interference signal when the path length changes. However, in order to retrieve the full phase information, we need another signal with a phase offset of 90 degrees. This can be implemented by retarding one portion of the wavefront by a quarter wavelength and adding a second detector in each arm. As we will see later, imperfections in the optical system and a slightly diverging beam are sufficient to generate a phase offset within each beam. So in practice, we only need to add 2 additional detectors. Now let's take a look at how this design concept can be implemented in practice. On the left, you see the schematic from the previous slide, and on the right, the matching physical layout is shown with simulated beam paths computed in Blender using the LuxCore renderer. You may pause the video here and take a moment to study how they relate to one another. Note that the beams are stacked vertically, which reduces the overall size of the interferometer. As you can see, it is hard to visualize the beam paths using 2D images alone, so I quickly jump into Blender to show an animation of the beam paths in 3D. On the screen, you see a model of the interferometer's optical train. We have the laser, the 4 detectors, the 3-corner cube reflectors, and the beam splitter plate. When running the animation, you can see the light beams emerge and observe how they split and recombine. The corner cube reflectors move the beams from the lower level to the upper one or vice versa. I will play the animation a couple of times now from different perspectives. At the end of this video, I want to show a few clips of the optical train in action. Further details about the case, the alignment, the build, and the construction are going to be covered in one of the next parts of this video series. For now, my goal is to give you a first impression of the interferometer, how the presented ideas are realized in practice, and what the interference signal looks like at the detector locations. Shown on the screen now is the top view of the interferometer with its optical components. The strength of this design lies in its simplicity and the absence of expensive parts. The test setup consists of a steel base, the device itself, and a moving sled holding the reflector of the measurement arm. First, let's take a look at the signal from the measurement arm. When pressing lightly against the sled, the path length changes and a brightness signal is produced through interference. Each blinking cycle corresponds to a length difference of about 250 nanometer. In future, 2 photodiodes will be placed at the location of the blinking spot. Similarly, we can look at the signal from the stabilization arm. Using a lens, the beam can be expanded to get a magnified image of the interference pattern. You can imagine how placing 2 photodiodes at different locations within the beam produces 2 phase-shifted signals. As this video was already quite dense in information, I want to conclude with some images and beam shots. If you sticked around until now, I thank you for your curiosity and for watching the whole thing. Stay tuned for the next parts of this series, where I'll share further progress on the project. I will also share some great resources in the video description if you are interested in this kind of topics.